Morning, folks. So, a week or so ago, I wrote a Piazza note asking if anybody had any feeling about lectures for next semester, and of course nobody wrote back because that's a semester away. But what do you think about the idea of replacing one or more lectures a week with lab sessions? And the idea would be that in that lab session there would be a checkpoint for the lab, the current lab. So there'd be effectively a required exercise for the lab period. That seemed like a reasonable thing to do. Any opinion on that? Yes.
The downside of checkpoints is, under some reasonable development schemes, nothing works until the last day, and then everything all comes together.
That's true. That's very true. That there are certain kinds of development that suggest that you have everything flowing down and nothing works until you all put it together. But it's very hair-raising to do that. I end up chewing on the wall every 2 weeks in this class because of it doesn't seem like anything's getting done. It's not getting done. Suddenly it's done, which means that there are a lot of people who were up all night for 2 days or 3 days. And I'd like to avoid that if I could. What about looking at lectures on YouTube and then coming in? Are people okay with that? Would they actually look at them? No. So that wouldn't work. So there is the one good thing about lectures is there's some economy of scale. I get to talk to all of you at once. Half of you at once, anyway. And without lectures, there's no way of getting that economy of scale except to write lots of Piazza notes, which then you wouldn't read, because the more there are, the less you read. So I'm not quite sure how to do this, but if you have any thoughts about it, I'd love to hear it, either now or in email or whatever. As far as this semester goes, I thought I'd talk today about some stuff I've already written that could be usable for or useful for final projects. So you don't reinvent the wheel by, say, rewriting DSP, which I saw people doing last semester in 4760. And I want to talk a little bit about what the infrastructure that exists, and then I'll be happy to talk about anything else you want, or I'd also be perfectly happy to just go to the lab and we can spend the rest of the semester meeting in the lab. What are your thoughts on this? Lab? More talk after today? What's the scoop?
It's probably pretty late to invite people with guest lectures on related topics.
It's hard to invite people, and that would be useful. I mean, I'd like to hear from Zhang about high-level tools, for instance, and maybe sooner or later I will. Probably should take his course. And but I don't think that that's feasible for this semester. I think it's too late for that. But what do you think? Who has an opinion? Lab time? More lab time, less lecture time. Okay, so then today I want to just talk about some of the general stuff that exists already on the course site. And in particular, for the last few days, I've been messing with memory models and how to run VGA effectively. And there's two separate use models that both make sense under different circumstances. One is put the VGA buffer in SD-RAM. By the way, the default university computer puts part of it in SD-RAM and part of it in on-chip RAM, and I'm not sure why. So either put it in SD-RAM or put it in SRAM. The advantage of SD-RAM is it's inexpensive. It's off chip. And so the real estate is not very worth very much. SRAM is on chip, and the VGA buffer uses about 50% of the SRAM on chip. So you're taking a big hit on the on-chip SRAM. On the other hand, this is single-threaded, and through QSYS, the maximum rate you can write this with VGA still updating is about 6 million transactions per second. So let's call it 6 million pixels per second, or if you pack pixels into 32 bits, it might be as high as 30 million or 24 million pixels per second. On chip memory, you can write as fast as your state machine will run. So you could easily get 50 to 100 million pixels per second written, as long as you set up the SRAM to be dual port so that VGA gets access all the time to one port and your state machine gets access all the time to another port, which then don't interact. So the SRAM solution uses a lot of memory, but it's really fast. SDRAM uses no on-chip memory, but it's okay fast, not hugely fast. Yeah?
Is there an order ID that exists for SDRAM that does not use QSYS?
Yes, there is. You can write your own you can write your own SDRAM controller. I believe in the university IP there is a dedicated SDRAM controller. And if you use that, you can probably go up, again, about a factor of 10 in writing speed.
Over the QSYS?
Over QSYS, right. It is, however, single-ported. So you can't do the trick of high input into one port and high output out of another port for the VGA. So, unable to update, thank you. So, I finally documented this stuff. We go down to the Avalon Busmaster peripheral. There's a section here now that uses VGA display. It uses a Busmaster as a GPU and displays from SDRAM, and then another section that uses the same HPS code with the same function that the FPGA is a GPU for rectangles. It's boring, but it's fast. And the only difference is that this section is displaying from SRAM and the top one is displaying from SDRAM. Turns out there's a little bit of a tweak, and that is that SDRAM, you have so much SDRAM you don't care if you waste a little bit of memory. So you put it in XY mode, and X is 10 bits, but you're only using 640 codes out of 1024, so you're losing over 30% of the memory because you have lots of vacant spot. To use SRAM, which is a sparse resource, you don't want to waste 30%. So you put the VGA into sequential address mode. And the only change in the code is that the shift by 10 bits to insert Y into the right address becomes a multiply by 640 instead of a shift by 10 bits. The downside is, oh wait, I can't think of any downside. Because a multiply is the same speed as a shift on the ARM architecture, more or less, within a cycle or so. And multiply by a constant on the FPGA does not necessarily instantiate a multiplier. It just uses the right bit weighting to do it and instantiates a bunch of adders. So why not do that? So this mode is this GPU with fast display from SRAM uses sequential addressing, which means everything has to be changed in the way that the HPS works. And so I parameterized it and made a single point that has to be modified in the HPS code. And that is that for the, why can't I zoom this today? Oh, different browser. That sucks. Okay, let me go back to the Safari browser. That's better. So for packed VGA memory, now the address, the pixel pointer is given by y times 640 instead of y shifted 10 bits. That's the only change, but that is the only point in the code that now has to be changed to shift back and forth between packed and sequent and XY. So there's two memory models. Use the one that fits your project the best. Do you need brute speed, but you don't need much memory for other things? Or do you need lots of memory? Some people are interested in doing video input, video capture. This charming picture of me sitting at my desk trying to simultaneously flip a switch and take a picture is overlaid on graphics being drawn by the HPS. So the disks are being drawn by the HPS. The video is being captured by the NTSC television input port, which is hardware on the board, and is being displayed, is being copied from the input port directly into static RAM, where it is then copied into SDRAM by hardware. If you need video input, you can just grab the image from the SRAM and use it. It's a dual ported memory. You can just reach in and grab that image out and do anything you want with it.
Which does this mean this is using of the it's like duplicating it, isn't it? It's using of SRAM and SDRAM?
So it's using SRAM to record the incoming television and SDRAM to output the VGA.
How big is the SRAM? What is it?
70 kilobytes, 320 by 240. Under some circumstances, you can merge them. Some circumstances, you can't. So if I had been smart enough at the time to use a SRAM VGA display and write into that same dual-ported memory from the television capture, I could have done it all on-chip SRAM.
Possible to do it all on SDRAM?
I'm not sure. The reason is that you have a rather high write rate for the VGA that is competing against a read rate for the VGA, which is competing against a rather high write rate for the video capture. And there may be artifacts, although I have not experimented with setting the bus arbitration share to favor the VGA. There's lots of parameters here push back and forth. I just haven't had time to do them all. So you could experiment with that. So there's some VGA or some NTSC capture that's already been done. Some optimization for display, but there's some other stuff that I don't know if you had a chance to look at. I've been playing around with DSP a little bit. There's one group was interested in doing some sort of speech analysis, and it's a really good idea to read the literature on speech analysis before you try and do it. But one of the central concepts is the MEL spectrum, which uses the psychophysical principle that your ears are not linear Fourier transformers, but rather logarithmically distributed frequency analyzers. And therefore, if you want to capture the correct kind of information with minimum bandwidth that corresponds to what you use in your head, in your ear, is you should build a set of filters which follow a MEL scale. And so I wrote one of these because I wanted to play with it. So this is a MEL filter bank. It's got 32 filters. They're each second order bandpass filters. And at low frequency, you can see that they're linearly spaced about every 100 hertz or so. And at high frequencies, they are logarithmically spaced. And they are in fact distributed according to a MEL distribution, which you can slurp from the MATLAB code, which is linked up here. It's a fairly funky formula I got, of course, from Wikipedia, like everybody else does, and then synthesized into MATLAB. But you can certainly use that. So one thing I've wanted to do is, particularly for a pitch shifter, is you analyze the voice into those 32 MEL channels, and then you play back a sine wave proportional to the amplitude of each input energy, but you shift the sine wave frequency slightly and you get a shifted output. So this is my voice played back through as 32 sine waves. So that's pretty understandable. But that's a good place to start for capturing what you need to capture to understand voice. You would then take the MEL coefficients, you'd square them or take the absolute value and low pass filter them, and come out with then a series of energies, 32 different energies profiles for each word through each filter. So it would be the power over time through each filter. That gives you a data set that's fairly low dimensional, it's fairly low rate, and which is moderately unique for each word. So that might be a piece that you can carry out on the FPGA before you send the data over to the HPS for serious analysis. Oh yes, but there's generally audio loopback is documented here, and I wrote a decimator which allows you to convert from 48 kilohertz to 8 kilohertz. The decimation filter attenuates the 48 kilohertz signal at 4 kilohertz, which you have for an 8 kilohertz bandwidth, so you don't get too much aliasing. So that's the slightly ugly filter form for the decimation filter. Then you drop the filter rate to 8 kilohertz. All of the computation requirements drop by a factor of 6, and building the filters is easier. So decimation filters I have running. But in fact, if we scroll down slightly past the break to the older pages, I wrote a ton of filters for the DE2, which are just Verilog, and so they run on the DE1, including 8-bit fixed point, 27-bit fixed point. Those are good for audio rate. If you decide you're going to do real-time filtering of a video signal at 30 megasamples per second, then you need to go to a parallel pipeline version, which runs at bus rate at 50 or 100 megahertz, and you can systolically pump data through that all day long and at full bus rate at video rate. Many of the students in past projects have done 2D filters for video. So let's say that you want to find the edges in a video image. You might take the image, the VGA image, and put a small convolution kernel at every point on the image. And for a first derivative, the convolution kernel might be subtract all of the pixels on the left from all of the pixels on the right, and that'll give you the approximation of the first derivative in the x direction, and do the same thing for the y direction. To get an edge detection, so to make an edge image, which will give you the outline of, say, a face or a hand. And you can pipeline the image analysis so that this image, the multiplication by these two arrays happens at pixel rate. You can make it completely real time at VGA rate. It requires a pipeline that is 3 lines long, so you can get nearest neighbors. Well, that's only 1,800 bytes or so. That's easy. So there are various kinds of mostly IIR filters. A fixed point CIC cascaded integrator comb, which is a better form of a decimation filter. Soft radio transmitters, think twice before you build those. They're illegal. Carpless strong string synthesis. So there's some examples of how you use a memory block as a shift register, but remember that there is a shift register primitive in Quartus that allows you to build arbitrary length shift registers, which is probably what you want to use rather than my hacked together memory block. Also some sections on direct digital synthesis you've already done. Noise synthesis. It's really nice when you have video game to make a sound so that you can represent broadband events represented by white noise. And in fact, for the Carpless strong algorithm for string synthesis, if you want a plucking sound, You have to put energy into the string, broadband energy, and the best broadband energy, well, what's broadband energy on a string? It would be an impulse function on the string. Hard to get a lot of energy into the string that way because if you make this very high, your arithmetic will become nonlinear. But broadband energy can also be white noise distributed over the string. It's just the phase is different. The only difference between this signal and that signal, if this is broadband white noise, is the phase of the sine waves. Your ear is phase insensitive, more or less. So one way to drive a string is to start it with white noise on it. And some adaptive noise cancellation and some other stuff. So those are already written. I'll be happy to discuss those with whoever needs it. We've already talked about floating point. There's some information on, more information on generation of sounds. A couple of small CPUs, if you're into small CPUs or you want to hack together a CPU to do some small task, you don't necessarily have to write it yourself. We've already written some of those. RS-232 transmitter interface. Let's say you want to send data back from the FPGA to the PC. One way to do it would be serial, RS-232. On this architecture, though, my guess is that you would use UDP. Much faster. UDP is, oh yes, is documented. Where? On the university computer page, down towards the bottom, there's a scheme from MATLAB through the ARM to the FPGA, and you go either way on this. UDP is extremely easy to set up because it's just Linux. There's a whole library for supporting Ethernet UDP. You get Ethernet rates. Pretty handy. Probably a good idea if you do that, though, to start worrying about inter-process communication, IPC, so that you can spawn a thread that does the UDP communication, but does not block other computation. In a fit of boredom one summer, I wrote this thing which uses rolling dice to solve chemical kinetics equations, because after all, at some low level, molecules hit and either stick or fall apart. And the hit versus stick fall apart may as well be a random process because it depends on lots of degrees of freedom of the orientation of one molecule against another. So you can completely throw away the differential equations and simulate it by throwing dice for each interaction. And the only trick is to make the dice good enough that you don't start getting correlations. And the Oregonator is a particular kind of chemical oscillator that was invented in Oregon. So I was using it as an example. But the main reason for bringing this up is I wrote a pretty good quality random number generator based upon a 1970s physical review article, and it is a 127-bit linear feedback shift register. So it repeats every 2 to the 127th ticks of the clock. So that's about every 10 to the 40th time ticks. And so at 10 to the 8th per second, that's about 10 to the 32 seconds, which is a great deal more than the age of the universe. So effectively, this never repeats. But it's folded in such a way that you get a 32-bit output on every 2 clock cycles. So you can put out a lot of independent numbers if you need a lot of independent random numbers. It passes. I haven't done extensive testing on my implementation, but it passes kind of the 0th order approximation for random numbers. Seems to be uncorrelated. So there's low precision random numbers and then high precision random numbers that are already written. And you can see some interesting things. If you have just a few molecules, then the system is dominated by Poisson noise, and you see these waveforms. The black lines are the ODE solution. If you go to a few thousand molecules, the statistical output converges to the ODEs, as you would hope. And so the black lines overlap the colored lines almost exactly. So that was kind of amusing to do. Oh, and in the process, I wrote the serial transmitter so I could get data back to MATLAB. This was in the days before we had UDP on the processor chip. So before you do a lot of inventing the wheel, come talk about it. If you need some algorithm, it may be that some student has already written it. It may be that I've written it. It may be that there's existing IP. For instance, there's an FFT generator that comes with the distribution. You can convert an FFT, you can convert a Fourier transform into a Mel spectrum by combining bins. Maybe that's worth doing, rather than writing a filter bank. But come talk. You've got plenty to invent without redoing the wheels. Any questions? I've thought for a long time that I ought to tag final projects by the techniques that they use, but I never have. I probably should start. So ambient light from TV signal suggests that there's some sort of global color analysis of the incoming signal. Camera-based fingertip detection is a combination of video input and a bunch of morphological operations to look at the curvature of a fingertip and figure out where it is and use it to control a video game. Audio signal visualization was an attempt to convert music to graphics. RGB LED matrix audio visualizer is really an exercise in
I'm Sam. I'm sure.
Is seeing how fast you can. So seeing how fast you can. And you have a little bit of diffuser over the LEDs there, right?
Yeah, that's a parchment paper.
How fast you can run a matrix, a 64 by 64 matrix of LEDs, and because you have so much brute I/O on these boxes, you can do quite reasonable animation, even though you're outputting lots of channels. Levitating a ball was an effort to have a high-speed controller lifting a steel ball off the table and holding it in space using an electromagnet. So it's some power electronics, it's high-speed control loop, some PID controllers, and some graphics to debug the whole thing. Gesture Tetris, I don't even remember what that is. Oh, that's right. steering it by moving your hands. So this was doing skin color detection. So this is detecting the color of the student's hands, and she thoughtfully wore a purple sweatshirt that looks nothing like skin color to help isolate her hands. Cricket 2007 auto batter. This was a it was one of those projects which was so hard I was sure it wasn't going to work, except they got it working. And so they had to watch a VGA signal, which meant they had to build a custom board for doing the high-speed ADC on 3 channels, and hook that all built. So they built a circuit board, hooked it to the FPGA, and came up with an algorithm watching the television signal to swing the cricket bat optimally to make lots of runs. And it was inhumanly good. Evolution game I don't want to talk about. Table tennis tracker got, so they figured out a way of setting up a ping pong table in the MEng lounge. It annoyed a lot of the MEng students. But the FPGA could track the green ball. I don't know if we can see it on here or not. Ah, there it is. That's the video, and it's automatically detecting the trajectory of the ball and what's happening with the ball. That made a whole bunch of websites, including IEEE Computer, as a one-pager describing the project. A Rubik's Cube solver with little mechanical hands that rotated the Rubik's Cube. Oh, video analysis. One of my favorites was the gravity end particle simulator, because I like computational physics. And this did rock, paper, scissors, detected the shape of your hand, and I think didn't cheat. Gesture control of an iPhone. Mandelbrot color modulation. Inventing the personal computer. Yeah, they didn't get too far on that. So this one was hilarious. Fruit Ninja with video tracking. You could so it was tracking your hand very reliably with lots of faces and other stuff in the background. And what you were trying to do is to slice fruit in half before it flew off the screen. And we managed to spoof it finally by doing a sort of a quick change out from fist to face by running your fist up over somebody's face and then pulling their fist away, and it started tracking their face. But it's really quite good at rejecting noise and finding the centroid of the hand. Flappy Bird Player was awfully hard to get moving. Bruce in a box. Oh, yes. So Julie Wong made a device that would track a green square on the screen, make an estimate of its size and orientation, and render stuff onto the. So there's me rendered onto the. She's having a little too much fun with this. Interrupt, a couple of hardware processor kind of things, hardware Ethernet implementation. Nobody in their right mind would do that now. Egg Crusher game, that was truly strange. Upper body motion tracking. This is pretty cool.
Tell me about your upper body tracker.
Okay, so a real-time video feed coming from this camera, and here is a downsampled version, average version of all the pixels that qualify as skin pixels. So as you can see, it's tracking my head and my hands pretty clean. Projection of the head tilts. That's computed based on the centroid of the head, and the body just follows the head. And I could do things like, and they're all updated simultaneously, so you could do things like, it could be like a future extension of the project if somebody were to, continue.
So it's parsed into hand and head, and then resynthesized as a 3D line element there. NTSC battle game, augmented. Oh, this was very cool. So what they did was they.
Okay, so what we did was we made
Using edge detection and other techniques to convert that into a line image that you can then use as a maze.
Exactly.
So you can draw like any kind of map just in a matter of seconds.
So what you can't see from this is that the.
That's right.
Is that and if you walk into the lab now and look at the left end of the lab, you'll see that maze still on the board. Because what they did was they just took a video camera and pointed it at the whiteboard. You drew whatever maze you wanted on the whiteboard, and then their algorithm would fire balls into the new maze. You could modify the maze on the fly to make it easier or harder, right? And so it was kind of a mixed reality, augmented reality maze thing, where the dynamics was controlled by the computer, but the maze is just hand drawn. And the hardest thing was getting the lines and getting them noise free, because they're all different intensities and different widths and ugly, and they managed to make them all look like solid barriers. Let me see if I can show you.
Close. Oh,
okay, got
it was
it.
Rob. Very nice.
We can also show the effect of increasing the threshold.
For edge detection, so we can increase the threshold, try to eliminate some of the specks.
Then the only consequence is you might lose some of the
Lines.
I see. So you might.
I wanted to try and find the picture.
Okay.
Oh,
so
that's
get the threshold down a little bit.
that's the one of the that's a human with the same
That's
algorithm.
an evil-looking face, but the eyeballs really stick out. Okay, give me a different threshold now.
All right, let's go up a little bit. So you can't really see all the features, but you can still see like the outlines.
Right.
So it really depends on the application.
Yeah.
If you want to see details, you probably aren't going to want to use it.
So there's the camera.
It's taking a video of the board over there.
I see. So you just freehand drew a map on the board.
Exactly.
And then you're using edge detection and other techniques to convert that into a line image that you can then use as a maze.
Exactly. So you can draw like any.
That's cool. Anti-Tetris, very odd. Video game enhancer allowed you to do split screen on commodity video games. Hardware-based AI for Super Mario Brothers. It turns out that's a hard thing to do. They managed to get it to some extent. Beat programmable gate array. Piano Hero with virtual keyboard. Prime number generator and RSA encryptor, decryptor. They were breaking passwords like crazy. It had like 40 RSA brute force searchers going. Oh yes, I have to show you one more. Falling Sand game. This is a cellular automaton done by Skylar Schneider.
So I've created a falling sand screen. Is basically
Let me move up to it.
Cellular.
So every point on the
You can see that the sand starts to form a pile. Similarly, you can start drawing here to split the water. Now I can show you a bit about how these particles interact with each other. So, for example, if I take the salt and the water here, they will mix together. The Water will mix with the salt to make it wet, make salt water. Sand is insoluble in water, it will sink to the bottom. Similarly, if I form a nice pool of oil here and try to drop some water into it, the oil rises to the top of the water. On the other hand, I draw a wall to connect the salt and the oil. There's really no preference for one over the other. They don't sink into one another. They just kind of form their own piles. The same thing.
So this is doing a 640 by 480 automaton with fairly complicated rules at full video rate. He spent a long time with pencil and paper doing the timing diagrams for that to show that he could get all of the cycles fit in that he needed for each pixel. So it's a very interesting staggered pipeline to do that. So I strongly suggest you take a look at some of these examples, because it'll give you some idea how to hook stuff up. Real-time face tracking, green screen chroma keying for being your own weather person, 2D graphic, guitar synthesis, speaker recognition. They managed to, the two students managed to most of the time get the FPGA to tell who is speaking. The general algorithm for that, by the way, is to take the Mel spectrum. So you have 32 points coming out. You take the discrete cosine transform of the Mel spectrum. So you take the spectrum of a spectrum, and the lowest 12 coefficients of the cosine transform of the Mel transform are highly predictive of who is speaking. It's called, by the way, it's the spectrum is sepstrum. It's called the Mel sepstrum. It's the cosine transform of the Mel spectrum, and you can, by doing some training on a network, you can figure out who's speaking from those parameters, which somehow represent the shape of your throat, size and shape of your throat. So, any questions? I mean, there's lots of stuff to look through, but again, the main thing about what I'm trying to get to here is talk to me or look at the web page before you start reinventing algorithms. So we could try and expedite some of the final project, make it more efficient to do the final project development. Okay? So, as of Wednesday, we are done here. We will be in lab. Starting this Wednesday. Starting this Wednesday, we'll be in lab. So thank you, Video Note. And exactly 0 of you have signed a release for the video from last week. Therefore, none of the video will be up. Monday was the deadline for that. Is anybody actually going to do the release or no? All right, no. Okay, well, I guess we'll pass on that. All right, thanks.